Okay. Hey, so today I wanted to go over the security for CMA security of signatures based on trapdoor permutation that is avoids the random oracle magic and works in the standard model. So let me first set up the generic problem. So if you have any signature scheme based on the trapdoor permutation, then you generate the secret public key pair. In the case of RSA, right, this is an RSA modulus and exponent, and the secret key is the inverse. And adversary gets the public key, which defines the trapdoor permutation FPK, right? He can get any message signed of his liking, and the signature oracle has to sign it, and somehow this computation intuitively must involve basically computing the inverse of this trapdoor permutation on some input, right? Because, well, otherwise, how would you, a signature is somehow a proof that you have the trapdoor so that you can compute the inverse of this function. Somehow, signature must involve such computation. And then when the adversary forges, right, he gives a message signature pair such that the message is different from all these pre-signed ones, right? And somehow, okay. And verification of this involves computing the FPK forward, right? So how would the proof work? Because if we have a reduction which gets the public key, and say a random point in the range of this trapdoor permutation, well, the reduction would embed this public key, would just pass this public key to the attacker. But how can it perform the signatures, right? And well, somehow it must, right here, it must simulate. Simulate what? This is called simulate signing. So it must be able to compute these messages in some way that avoids knowing the trapdoors. Okay, and somehow from the forgery, so that's the first task of the reduction, is this simulation of signing, and the second one is extraction of basically the challenge, right, which is sorry about that. Extraction of the challenge computation from the forgery. And we have seen how to do this in the random oracle world by preceding these, basically allowing these two stages by embedding trapdoors into public key generation. So somehow the public key, the reduction is that it embeds some trapdoors that allow both simulation of signing and extraction of the right. So what has to compute is B such that FPK of B is A, right? So extraction of this pre-image computation into the public parameters. Okay, but what other parameters A gets except of the public key, right? So let's see what has happened. So the example we have seen is the full domain hash RSA in the random oracle model for hash. And what has happened there? The arrow hash was the trapdoor of R, right? It let R embed. Why is the random oracle a trapdoor? Because it lets R embed. So for two reasons. First, R sees any query of A to H, right? Because H is this random oracle in the sky. A cannot compute any values related to H unless it queries them, except for negligible probability of guessing these outputs. And two, R can set H outputs at will, as long as they look random, right? But they might be generated, so they look random, but they have some trapdoors in them. And particularly, that's what we see last time. Whenever A queries H, the reduction decides whether to simulate H output to either embed some trapdoors that later allows signing such a message, or embed a trapdoor that allows extraction of the pre-image of A from signature on A. So let's see how to do this without the, in the real world, not in the world where you imagine that a non-deterministic hash function like SHA is a random oracle. Okay. So RSA TDP based signatures without arrow. There is many results. So the first was by Kramer-Schupp, 99, Gennaro, Halevi, Rabin, Senier, Tishlin, 03, Hofheinz, Kilt, 08. They all avoid, but they all have a stronger version of RSA assumption. Some of them additional requirements on age, although most just assume collision resistance, which is quite okay. And all modify FDH RSA. So it's somewhat longer and slower. Okay, so the signatures are longer and they're slower to generate and to verify. The search, in some sense, continues, right? Because it's there is no. I mean, they're still longer and still slower than standard RSA. But not as crucial because, first of all, bilinear maps, so elliptic curves with bilinear maps basically give shorter and faster signatures. And again, in this world, it's a similar thing of with the arrow, we have very fast, very simple constructions. And again, we would like to get rid of arrow for those, right? So it's a similar search for optimal constructions. The point is that it is more important here because asymptotically, RSA is going to grow and become even more expensive compared to elliptic curve signatures as the time goes by. And so elliptic curve arithmetic gets better and better implementations, and it's just more focused on it. And unless there are some big breaks in the elliptic curve world, then that will somehow rebalance this. This is for now looks like a more attractive setting. And lastly, lattice-based signatures are, in a sense, even more important because they hope for security post-quantum. Right. So what is the stronger version of RSA assumption? It's called so-called strong RSA assumption, which, as far as I know, all these schemes, I mean, these for sure, and also anything else that tries to avoid arrow, to the best of my knowledge, is strong RSA assumption, which goes like this: for every efficient algorithms A, probability that A given just modulus, RSA modulus, and a random point in the RSA domain outputs pre-image together with the exponent. So B has to satisfy this requirement, right? And E has to be non-trivial, so it's at least 2. That this is negligible, where N is an RSA modulus, and A is random in star. Okay, so unlike the standard RSA, the point is right here that adversary chooses E. So therefore, standard RSA says computing these roots is hard, and strong RSA assumption says that computing any root is hard. Okay, so you can, given a point in RSA domain, an attacker succeeds if it finds any non-trivial root of this point A, right? Which root it has to be, whether it's third or 17th or second, right? For RSA parameters, 2 is not an RSA parameter, but it's still a non-trivial root. In fact, computing second roots is equivalent to factoring. In this, this assumption says, even if you had a choice of which root you wanted, you can't do it. And we know of no weaknesses in this assumption apart from generic weaknesses of factor. Okay. Another thing that these schemes do is that it's a part of the making, basically saying a stronger RSA assumption is that the RSA key generation is modified to generate so-called Safe RSA moduli. And the Safe RSA means that N is PQ for P, which is 2P prime plus 1, Q is 2Q prime plus 1, and PQ, P prime, Q prime are all prime. Okay. P prime, Q prime are of the same length, and therefore P and Q are of the same length, and this is polynomially security parameter. For example, 2048 or so bits. Okay, why this Safe RSA moduli? So the point is that why? So Z and star is not cyclic. And has subgroups of small orders, any divisors of phi of n, which is p minus 1, q minus 1, which, you know, is first of all even. Second, might have, so as we said, has subgroups basically might have subgroups of small order, because these, even if P and Q are prime, P minus 1, Q minus 1 can be smooth. Now, if P and Q, P minus 1 and Q minus 1 are smooth, that's an insecure setting. So RSA would be attackable on such. So if they're too smooth, a random prime is not smooth enough for the attack, for these attacks. But it's still, they might have small divisors, in particular 2, but you know, nothing stops them from being divisible by, so they're not divisible by E, right? So let's say E is 3, so you set them so that they're not, so they're coprime with 3, but maybe they are not coprime with 5 or with 7, etc. Right? And if you set them this way, then they will be, because if N is safe modulus, then phi of n is 2 p prime q prime. So 2 is the only small factor. Okay. The other factors are p prime and q prime, and if you define them, then you factor n. Now, why is that important? Okay, so these schemes would consider a reduced group of so-called quadratic residues. So these are quadratic residues mod n. In other words, elements that look like this for x in p and star, squares of other elements. And if n is safe, then the order of q or n is p prime q prime. So it's 1/4 of the order of z and star. So and q or n is cyclic. Okay, so what are the two nice consequences? Fact one is that because it has no small divisors, every small enough integer has a multiplicative inverse mod n prime, which is p prime q prime. Okay, so the order of this group is p prime q prime. I'm going to call it n prime, and that okay. And in if yeah, and any integers mod here will have a multiplicative inverse. Fact two, even though this is a secret order, if you knew p prime q prime, you would factor n. So a reduction cannot know this order. However, if so, first of all, a random a in q or n generates q or n, except for negligible probability. Why? Because the order is this. Okay, so the only way an integer might not generate the whole group if its order is either p prime or q prime, and that happens with the negligible probability for a random element in the group. Secondly, if I look at numbers like this for random integer r of size n plus security parameter, okay, they look statistically indistinguishable from random in QRN. Why? Because an integer of that size, its remainder modulo this unknown order. So you know that a to the r mod n is the same as a to the order of this group, the r modulo order of the group. The order of the group, if you are in QRN, then the order is p prime q prime. So this is equivalent to A to the R modulo P prime Q prime. But the integer is so long that the overhang from this modular reduction, in other words, the quotient, is itself an integer of length, at least the security parameter. So that's enough that the modular reduction is basically sampling almost uniform mod. The modular residue will be almost uniform in modulo of this model. Okay, so okay, now we will use this fact in reductions.
Professor?
Yeah.
I don't think I get the last part. Why is it uniform? Almost uniform?
Okay. Okay, so A to the R is A to the R mod P prime Q prime mod N. Okay, if R is a uniform integer from between 0 and n plus 2 to the security parameter. Okay, then R can be as R hat plus T times P prime Q prime, where this is R hat is just R mod P prime Q prime, right? So this is the remainder, and this is the quotient. So I mean, this is always the case, right? And the question is, what is the distribution? If you take an integer from this range, what is the distribution of R hat, which is R mod P prime Q prime?
Oh, I see. It's because the interval is a lot. It's yes. P prime Q prime times something big, right? So the last part won't matter that much if it's not in a boundary.
Exactly.
Okay, I get it. No, thank you.
And it's not going to be, because this is not an exact multiple of this number, right. But this is some multiple of P prime Q prime plus some overhang. This multiple is at least 2 to the security parameter. And this overhang is, well, it's smaller than P prime Q prime. So,
wait, why is it so big?
Because, oh, sorry, times.
Oh, okay.
Yeah, it's times. Yeah, so the length is the length of n plus security parameter. The value is n times the 2 to the security parameter.
Okay.
So if this was 0, then the number chosen from this range, modulo P prime Q prime, would be uniform, right? No matter what K1 is. So what is the fact that we are choosing from, not exact multiple? How much does it skew the distribution of this residue? So you can basically see that it cannot skew much, right? Because you are here are these exact multiples and of p prime q prime, 2 p prime q prime, 3 p prime q prime, and here is 2 to the security parameter p prime q prime, and here is some overhang, okay, k1, k2. If I choose a uniform number from this range, I can split it by, okay, the probability that I choose something from here, and if I do, then I'm perfectly uniform, my residue is perfectly uniform, plus the probability that I actually choose something from this region, in which case, well, it's not uniform. It could be like in the worst, like a half, or even smaller, right? But I'm just going to upper bound it by the probability that I even choose anything from this region at all. So the probability that I choose something from here is K2 divided by this whole, so the probability is smaller than this thing divided by this whole length, which is 2 to the security parameter, p prime q prime. Now, this is at most p prime q prime, and this is 2 to the security parameter, p prime q prime. So this is at most 2 to the minus security parameter, right? So, so therefore, the statistical distribution here is at most this far from perfectly uniform mode p prime q prime, right? Because this generation of a random r hat was like this. First of all, I had a choice of either picking something from here or picking something from here. And this region is so minuscule part, then the probability that I entered the second option was at most. Okay, so that's how you can see that it is the contribution that this region gives to the overall distribution is negligible. Okay.
Yeah, thank you.
Okay, so now okay, there's one more thing that that we want to okay, there's actually two useful tricks. First one is called Shamir trick. Addis Shamir co-inverter of RSA, and it does this. If someone finds C is such that C to the E is A to the Z mod n, then and GCD of EZ is 1, then you can extract if root of A mod n, namely set B to be A to the alpha, C to the beta, for alpha beta such that alpha E plus beta Z is 1. Okay, and this can be found by extended Euclidean algorithm. Right, so if you know that two integers are coprime, then extended Euclidean will not only confirm that, right, computing GCD, but it will find you these two coefficients which satisfy this equation. Okay, and why is this an e root of a? So check b to the e a alpha e beta to the e, which is a alpha e c beta e, and this is a alpha e c beta, but c to the e is a to the z, so this is a alpha e a z to the beta, and now I have alpha a plus zb in the exponents, so this is a, right? Mod n. Okay, so that will be useful. Basically, it says that in order to find eth root of a, it suffices to find eth root of any power of a, as long as that power is co-prime with e. Okay, and another thing you might avoid is that solving strong RSA on a random in this subgroup of quadratic residues implies solving strong RSA on a random a prime in N star. So the strong RSA assumption was defined as okay, solve RSA on, what does it mean? Any random and a mod n, right? The co-prime with n. If we solve it for a random quadratic residue, well, this thing is, so many ways to see it. First of all, random element in N star is in QRN with probability 1/4. But perhaps, yes, right? So if you can solve its roots, compute roots of these guys, then you are going to, at least with 1/4 probability, compute its roots on elements like this. Well, and another thing is that set A to be A prime square. Okay, and now A is in quadratic residue, and in fact, it's a random element in quadratic residue if A prime is the random Z star element. So if somebody finds an eth root for E different than A, then using this trick, you're going to find eth root of A prime. Now, what about if it's equal to A? Well, finding square root of A allows factoring, except of with 1/2 probability. So this is C Rabin cryptosystem. This is in Katzlander textbook. It's like RSA with E equal 2, but quote unquote, because you can't exactly do it because the decryption works differently and the whole encryption is less efficient, but it's the CPA encryption secure under factoring. So it's less efficient than RSA, but its security is based on factoring because decryption is like finding square roots, and it's a nice trick that given a random an algorithm that computes square roots, you can factor RSA. So just check it there. It's the same argument here. Okay, so let's use these to create a CMA secure signature scheme without random oracles. So so here is the Fishlin O3 construction. It assumes a collision-resistant hash H onto we'll use this some lambda bit strings. The public key is RSA modulus and 3 group elements such that N is safe RSA, X, H1, H2 are all random elements in this quadratic residue subgroup. And moreover, the length of P prime Q prime is must be greater than the length of this hash function output, but that's standard because the hash function will be maybe 160 or 256, right? While these guys are at least 2000 bit long for RSA to execute. Okay, so they're larger, these prime factors anyway than the length of the hash function output. And the secret key is factors of N. The signature on M is sigma, which is a triple Y alpha, which satisfy the equation, verification equation y to the e is x times h1 to the alpha times h2 to alpha XOR hash of m, where alpha is a random lambda bit string. So this is an XOR between 2 lambda bit strings. And they are treated as integers, right, which define this exponentiation. And E is a random alpha lambda plus 1 bit prime. But it's not checked in verification. Only checked that E is odd. So, which is great because in verification I don't have to have primality checking. Be annoying. And node primes can be primes E can be pre-computed. So if you have an implementation application that signs all the time, this is maybe not so useful, but typically we sign and then there is like a pause and next signature comes along after some time. In that time we can run primality generation to generate these, and they're not so long, right? So they only have to be like 257 bits. Okay, so it's not generating 2000 bit primes. And once you pre-computed these primes so that you can generate a few signatures, what is the efficiency? Well, you have to compute the ETH root of this, but yeah, so that's computing roots, right? Which is basically inverting mod phi of n, which you have because your secret keys are factors. So it is roughly the cost of RSA signature to generate this, because this is so-called multi-exponentiation. So you can compute it in roughly the same time as exponentiation. So for NE, you compute G, which is the inverse, right? And you actually, the signer would pick H1 and H2 as powers of X, so that all of this is X to some power. And so computing signature is just exponentiation based X. Okay, so with H1 set as X to S1 and H2 X to S2 for random S1, S2, signature generation is basically X of X mod n, and so therefore it's basically like RSA signature. So with this pre-computation, signature is as fast, but verification slower, right? Because verification in standard RSA is just computing small power. And while here I have a multi-exponentiation to 160-bit value or 256-bit value. Okay, so that's many more multiplications than an RSA case where E is 317 or just has 16 bits at most, right, or something like that. And of course, signature is longer. It's not much longer because Y is the value mod n, so that is like standard RSA, while these guys are at most 2 lambda bits, right? So this is 2000 bits, and this is 512. Okay, so by 25% only. Okay, so actually the length is not such a big deal, but the verification, right? So you get pretty close, but of course this is annoying, right? So, and the pre-computation is not for everyone. Okay, now why is that secure? So Fishman shows that this signature is CMA secure under Strong RSA and CRH, collision resistant hash assumption for hash edge. How would we show? We will prove it by attacking the Strong RSA assumption, assuming a CMA attacker on the signature scheme. And intuition is that IR embeds trapdoors in PK, which allow, first of all, simulation of signatures, of signature generation and extraction of Strong RSA break from forgery, from adversary's signature forgery. Okay, but this embedding customize for different types, forgery types. So we will consider different cases of forgeries that satisfy certain equation given the previously signed messages. And for each forgery type, we'll have a different way of embedding trapdoors, which will allow this. Now, each adversary doesn't know which embedding are uses. So the embedding will have to generate uniform trapdoors no matter which forgery type is assumed. Therefore, the probability that a forgery is useful if you assume that with some non-negligible probability adversary is of a certain type. So there is, let's say, 3 types. If the overall chance of attack is epsilon, then if epsilon 1 is probability that he attacks and is of first type, epsilon 2 he attacks and is of second type, etc., then at least one of these epsilon i's have to be at most 1/3 of the epsilon, right? And now, so pick whichever one is non-negligible like this, then that reduction, which bets on the forger to be of that type, will succeed with the non-negligible probability for at least one attack type. Okay. Okay. So let's see what these attack types are, and let's see reductions for those cases. So attack type 1 okay. Okay, so I guess first some notation. Let sigma j, yj, ej, alpha j be signature on j's signature query mj. Okay, so it's a query made by A, right? A asks messages to be signed. Let's denote them within the mj, and let this be a signature on it, and let A's forgery be m sigma and sigma be ye alpha. Okay, and let q be the upper bound on the number of sig queries A makes. Okay, so now attack type 1. Attack type 1 is that the forgery is different from all the E's in the signatures. Okay, so right, a right, recall A queries the signature oracle on some messages MJ. The signatures are sigma j, and this is the forgery, right? So, and we're just considering the different types of forgeries depending on the signatures that adversary has seen during his chosen message attack. And let's say that the root in his forgery is different than the roots used in all the signatures. Okay, and we'll of course have a type which repeats one of the EJs in his forgery, right? So let's consider this type first. Okay, so okay, so first trapdoor generation. Right, so the reduction is given the Strong RSA challenge, N and A, and has to create this public key, but this public key will have the same N, but the reduction is free to pick all these guys, perhaps based on A. So it will embed A into all of them or some of them in order to be able to simulate signatures and to extract pre-image of A, but in a Strong RSA sense, so any root of A, from adversary's forgery. So the trapdoor generation here is pick, so R on input N and E, right? The Strong RSA challenge picks random primes of the length needed in the signature, E1 to EQ. So he prepares himself for all Q signature queries by preparing these EIs beforehand. And he sets H1 to be A to the product of all these EIs, X to be H1 exponentiated some more to some S1, and H2 to be that thing exponentiated to some other value for random S1, S2 of length, the length of the modulus plus security parameter. So here the point is, right, with long enough integers, these become indistinguishable from random, statistically quadratic residues if A is a quadratic residue groups generator, but we said it is. So a random A in a group of quadratic residues does generate this group, except for negligible probability. So we use all these here. So n sets pk, of course, to be n x h1 h2, and it looks statistically indistinguishable from a random public. Okay. So how do we sign? So signature simulation. To sign quote unquote MJ, R will use this J factor here, but it will pick random alpha J, and it will set yj to be the pre-image of J. So look, all these public key values are powers of A to the product of all EIs. So we can compute the pre-image of taking the, we can take EJ's root of this. It's just the product of A to all the EIs I not equal to J. In addition, additionally power of S1, additionally power of S2. And if the signature is the eth root of the product of these, then there's no problem, right? And if this is a product of with some additional exponent, again, not a problem. So this is what we do. We take A to all the powers that are needed. Here is H1 to the alpha. H1 is just A. Okay, so we take it to the alpha. And here we also take it to S2 because H2 has S2 in it. And the verification equation will have this. So we have to take it to this integer. And we take all of this to the product of EIs I not equal to J. Okay, and now you can see that a signature J is of course Yj, J, alpha J. Okay, and Ej is a random prime, alpha J is random generated S in the signature, and Yj satisfies the equation Y, right? Because Yj to Ej is all of this stuff is now I have all the primes. So it's A parallel to S1 times A product to alpha times A product all of the to the EJ to S2 and to alpha H of M, and now this is X, and this is H1, and this is H2. So the signature verification checks out, right? Okay. Okay, so now how do I extract from forgery? Extraction from forgery. Okay, so A gives outputs M sigma, which is YE alpha, such that this is correct, so verification works, and of course AM is not on MIs, and also by considering this attack type is different from all AIs. Okay. Okay. So note that if the verification equation works, so we have Y to the E is equal to X H1 alpha H2 alpha hash M, XOR hash M. And so this is because X, H1, and H2 are all set as basically powers of A to the product of all the EIs with additional factors in the case of X and H2. So this is all can be seen as A to the product of the EIs, and what are the extra stuff? So X has S1, so it's A to this times S1, and there is no extra power here, right? So it's just S1. Now, what about H1? Well, H1 is A to PI, but it's with extra power alpha. So we add it here. And what about H2? Well, it's A to all the PIs times S2. So we have to do this, but also to this stuff. So we multiply it by alpha XOR hash of M. Okay, and this is the exponent. So if I call this Z, then if GCD Z is 1, then using Shamir's trick, I get eth root of A, and therefore I get strong RSA break. Okay, so that's where the strong RSA, the Shamir's trick goes in. And well, I assumed this forgery type. So I assumed that E is co-prime with all these PIs. Okay, so far so good. However, Z is a product of all the EIs and this extra stuff. So this is true if attack is type 1 and GCD E prime is 1 for Z prime equal to S1 plus alpha plus S2 times alpha XOR hash of M. So, well, why should that adversary choose be co-prime with this value? Note, adversary chose alpha and chose M, so he chooses D and he chooses E. And all we know is that E is greater than 2, or actually, well, actually it's E is greater or equal to 3, because the only thing checked in the verification is supposed to be that E is odd, okay, and it's not 1, okay, and odd and greater than 1, right? Because otherwise each root, right? First root is just identity. Okay. So how come this number has a high probability of being co-prime with E? These are the two things adversary doesn't control, and that's not enough, because but also adversary has no info on S1 mod E and S2 mod E. Why is that? Okay, so first, if it was true that S1 mod E and S2 mod E are random, then this would suffice, right? Because if just the fact that S1 mod E is random suffices, let's say that S2 was even public, so he can set this in any way he wants, but Z prime mod E will be determined by S1 mod E. And if this is random, then S1 mod E is random. And so therefore, if as long as E is an odd integer, so if S1 mod E is statistically close to random, then probability that BCD Z prime is not 1 is well, it's the most 1/2. So let's say that E is just an E. Well, okay, probably less than that, but let's just say that E is greater or equal to 2. Okay, so the worst case is 2 or that E is even. And for S1, so basically consider any prime divisors of E. Okay, they have to be at least 3 because it's not odd. It's an odd number. Then probability that S1 mod that prime divisor of E is not 0 is at least 1 over that prime divisor, so it's at least that. And that works for all prime divisors. So why is it that he has no info? Well, it's the same argument as I used before. But so if S is a random integer of length p prime q prime plus security parameter, then S is S hat times p prime q prime plus basically S mod p prime q prime. What is that adversary sees about S1 and S2? Well, he sees some QRN element and other elements which are powers of H1 to these S values. Adversary gets basically what was this thing called? H1 to S1 and H2 to S2, but which reveal H1 to S1 mod P prime Q prime and H2 to S2 mod P prime Q prime, but S hat 1 and S2 hat are hidden. Okay, right? Because you don't know what these are, and again, they're not hidden perfectly because you're choosing the stuff not from a perfect multiple, but except from, I mean, statistically hidden. So you're getting information which is less than 2 to the minus security parameter Skew. Okay, so it's a negligible amount of information. So in other words, to any efficient attacker, you can just as well assume that they are uniform and therefore hidden from adversary's view. And what was a key issue in this attack? That it was is S1 mod E hidden? So S mod E will is S prime S hat P prime Q prime plus S mod P prime Q prime mod E. Now this is an information that is revealed to the adversary because of powers. Okay, so information theoretic. Of course, he has to compute discrete logs to in this group to really compute them, but this is an information theoretic argument. So let's say that we're just giving these out. This is still hidden. these numbers are coprime with E. So this implies that if S prime is random mod E, then S is random mod E. Okay, so therefore, probability that the GCD of S and E is not 1 is at most 1 over smallest prime factor of E, and this is definitely smaller than 1/2. This is the kind of algebraic trick that you are setting these numbers long enough, your trapdoors are long enough that the information visible to the adversary from these exponentiations leaves some modular residues of the same trapdoors, S1 and S2, information hidden from an attacker. And that suffices to argue that because they are hidden, so the chances that equations like this holds, must be non-negligible. Okay, that's all that was happening. Okay, I'm running over time, and I have and I have a second attack type to cover. So should we finish this? Do you have more time, or do you have to go?
I have time, but I'm not sure how the type 1 ended.
You mean this part, the extraction?
No, just distraction is fine. I just don't see what we concluded. Exactly.
What we concluded is that if you have an attacker of this type and he succeeds with probably epsilon.
Mm-hmm.
Okay, so let's call the overall success epsilon, and there's two types. So let's say that the probability that, okay, so let's call it epsilon 1, the probability that he succeeds and is of type 1. And let's say that epsilon 1 is non-negligible.
Mm-hmm.
Then this reduction, so therefore the probability that are successful is at least 1/3 times the probability that A succeeds and is of type 1. Okay, so if an attacker, given this public key and given access to the signature oracle, creates a forgery of type 1, so if this quantity is non-negligible, then the reduction gets the Strong RSA challenge, creates public key this way, signs quote unquote this way, and extracts RSA challenge from Strong RSA break from the forgery, except for this probability.
Mm-hmm.
Okay, so okay, let's make it 1/2. Okay. Okay, maybe this is 2/3. Okay, 1 minus. Okay, this 1 minus 1. Okay, so sorry, I'm writing 1/2 as 1 minus 1/3. Okay, so let's make it 2/3. Okay. Okay, so that are we fine now?
Yeah.
Okay. So let's look at the type 2, right? Which is, of course, that there exists a j such that E is j. Okay. I lost my own. Okay, now I have to find my notes, the pile of these pieces of paper. Okay. So the reduction, so how does he embed a tractor? So reduction on NA, first of all, guesses index j in random from 1 to q. Okay. Then he picks random p and w in QRN. You know what? Maybe one more thing about this first attack type. If we simplify this signature generation to simply a single base to hash of m, this forgery would work. This strategy would work. Okay, because the fact that there is a bunch of these base elements was immaterial here. What was material is that the end result is the verification equation of this type. That is the challenge to the product of the EIs, because right, it's a product of EIs times some linear equation. That linear equation has to have the the S value and some value related to the message. Okay, so maybe not. I could get rid of one of these and of this stuff. I would have two, and one of them would be just the challenge to the product of EIs, and the other would be the same with some shift S. And as long as the verification equation looks like this, S plus hash of M, so adversary chooses hash of M, but S has to be co-prime with E with a high probability. Okay, with this high enough probability. So the same argument would work. So if I consider this attack type, I could prove a signature of a simpler stuff. I wouldn't need alpha and I wouldn't need two elements. The reason why I have two elements here is to enable embedding, enable handling this case, okay, of reuse of the same root by the attacker. Okay, so okay, come back. Right. Okay, and then random long enough integer beta. okay, and sets H1 to be A to the product of EIs except J's, H2 to be V to the product of all EIs, and X to be this thing, so all the EIs except of the J's, 2 minus beta, and this is just so that some verification equation, further equations get simplified, to W to all the product of EIs. Why in this way? Okay, and of course, no public key, that to be n x h1 h2. The reduction would work only if its guess is correct. Okay, so the final reduction success will be 1 over q times epsilon 2. Okay, and perhaps some other losses. So it's not an exact tight reduction, but it still works. Okay, so let's look at the verification equation. Note that if I set public keys in this way, then the right-hand side of the verification equation, x to h1 alpha, h2 alpha hash h of n, is h, well, okay, so it's h1 to minus beta plus alpha, right? X is, I take this part, times v to, okay, no, how about w to the pi's. So that's part of h1 to alpha was already here, and okay, I'm just copying this, and now h1 was a to all the pi's except the j's, and that one was to alpha minus beta. Let me write it here. So it's a to the all product of all EIs except of J's times alpha minus beta times W to all the EIs times H2, which was V to all the EIs alpha XOR HN. And let me write it slightly differently. This to product of EIs. So all of this is supposed to be e to the y to the e. Okay. So how does the situation differ? Can we compute jth root of these type of values, right, for every j? Because we have to, we have to, in order to sign something, we have to create alpha and y and x and e, which would satisfy this equation. A was given to us as a challenge. W and V we picked. So these are 3 bases. Okay, and we only know all these exponents. So how do we compute an EI's root, EJ's root of this? Well, if very easy to compute ej's root of that, right? Because I just take the product of all the i's except of the j's. That's what I did before. What about this? I can do so for all i's except the j's, right? But the j's I is not here. Well, in the j's query, I just make alpha equal to beta. And therefore, this term vanishes. So I basically take ej's root of that, and that's my y. So this signature trapdoor that will be used on j's signature query. And these are trapdoors used on all signature queries, right? And this part is trapdoors used on all ice queries except I equal j, right? So that's where that's the point of. So I was arguing if type 1, if I had always attackers of type 1, this would suffice. Okay, the only reason to split this case into alpha and this is to allow this. Okay, allow an extra trapdoor in the case that the attacker reuses one of the j's. Okay. Okay, so
it doesn't matter that.
Mm-hmm. Yes.
So it doesn't matter that beta will be leaked, right? Otherwise, we could just take alpha equals beta plus a big multiple of.
What will be leaked?
Beta will be leaked, right? With the query.
Sorry. What will be leaked? Beta.
So you say alpha equals beta, so beta will be leaked to the adversary, but it doesn't really matter.
Okay. So look, signing. Okay. For all I not equal to j, sign like previous r. Okay, right, and set signature I to be yi ei alpha I, right? So just use this. For j's query, pick alpha to be beta, alpha j, and pick and then compute ej's root, of the right hand side, right? Because you can, because this cancels out, right? And
right.
This, of course, you can take ej's root for any, right? So what got leaked? Okay, this was used once, and beta is set at random. Now, was any information related to beta already visible in the public key? No, because this works like a one-time pad in QRN. If this is a random QRN element, that it masks out this one. That's the reason for it, really. Okay, so therefore beta is information theoretically hidden. public key. Okay, so this is a triple of random group elements independent of beta. Therefore, we can reveal beta in the J's quote-unquote signature, and it still looks good.
Right, and the betas will appear in the other queries, but alpha will cancel it out, right? Because alpha is now random. So in the other queries, yes, beta appears too, but alpha is going to conceal it.
Look, in the other queries, what do we leak? We leak EI, okay, but EI, it's independent of anything because these are random group elements. Okay, so okay, alpha is completely random.
Right. My point is that yi has some.
And yi is deterministic given this and the public key, because yi is EI's root of this equation. Okay, so yi by itself reveals no info. I mean, it's a deterministic function, so it doesn't matter how it's computed. But the only randomness is in EI and alpha I. And as long as they are independent, then yi looks exactly like the real signer. Okay, because it's a deterministic function given D. So it's only distribution of EI alpha I that you have to worry about. Alpha I is random in this way of signing. So it's only distribution of EI. So the question is EI visible in this stuff, right? And no, it is not, because A, V, and W were random group elements.
Right.
So it's the randomness in A, V, and W that already basically makes H1, H2, and X random. And the fact that adversary got, the A, V, W shifted by some known exponents. And then during the simulation, these exponents were all eventually revealed, right? E1, E2, E3, E4, so you reconstruct this. But so what? These points from which we started were random to begin with. So the fact that we shifted them by some eventually known exponents doesn't matter. Okay. So forgery, I think the forgery is very similar. By now, I basically don't remember anymore, but I mean, I have the notes for it. But it's a similar thing, because we are assuming that E is equal to EJ. Okay. So in a forgery, E is equal to EJ. No, so it is a little different. And now there's two subtypes. QA, E, the forgery is EJ, and alpha is not alpha J. Okay, and the second type is E is J, but and alpha is alpha J, but that implies that alpha hash M is not equal to alpha J XOR hash of MJ, because M must be different from MJ, right? Because it's the forgery, and CRA, and H is CRA. It's a collision resistant hash. So these two hash values must be different. So if alphas are the same, XORing them with hashes makes these two different. And that is the reason Fishlin sets alpha on one side and alpha XOR hash of m on the other. It's these two cases, 2a and 2b, are symmetric. We will show only for one case, but if you consider the other is completely symmetric, just switch the roles of H1 and H2. So in other words, make H1 this way and H2 this way. Okay. Nothing else will change. That's also the the beautiful thing in Fishlin. The only thing he needs is that either this exponent is different from previous use on this query, or this exponent is different. All he needs is that either this or that is different. And he gets it by this simple thing of taking any value adversary chooses and uses that value in the one exponent, and that value XOR hashes and hash of message in the other. Okay, so let's see, consider 2a, 2b is symmetric. Okay. Okay. Very hard to see anything. Is that to black out my shades, my window shades. Yeah. Hold on a second. Okay. High-tech solution, but okay, I'll try to come up with something better next time. Okay. So okay, so how do we deal with these forgeries? So when A outputs m sigma for m, of course, not equal to mj. So for sigma equal y alpha, and E is the same as EJ because this is our attacker type, and alpha is not equal to alpha j because it's the subtype. Then let's look. So this is the verification equation, right? So let's put x on one side and ye and all of this with the minus on the other. So ye h1 alpha h2 alpha XOR hash of m is x. But in the jth forgery, that was also the case. So this is also yj to ej, h1 to alpha j, h2 to alpha j XORed hash of mj. So of course we put all sorts of trapdoors into these values, but these equations are met. Oh, sorry, with the minus signs, right? Because we moved, I moved h1 and h2 to the left-hand side. So I have to invert the exponents. Okay, so let me see. Oh, fine, it's good. Note. I will drop out the x. I will just make look at the consequences of these two values being equal. And it is convenient for me to look at the following. So I'm going to put h2 and y's on one side. So h2 to the, now I'm putting this on this side, so I lose the minus. So it's alpha j XOR hash of mj. And here I have the minus, so it's minus alpha XOR hash of m. Okay, so I put h2 here. I also will have y and yj both to the e, right? Because ej is equal to e, so this is e. So I just put yj on this side, and all of this is equal to, and I keep h1 on the right hand side, so it's h1 to alpha minus alpha j. Okay, and here the key issue is that this is non-zero, right? By this this non-zero by this requirement. Okay. So okay, so what is this stuff? So because H2 is V2 a product of EJs, EIs, so this is EJ, right? And this is not zero. And H2 is something to the product of all the EIs. So I can represent this as, so this is V to the product of everything except of J to whatever this stuff is, so alpha j XOR hash of mj minus alpha XOR hash of m times y over yj, and I take all of this and I exponentiate it to ej, and I get this stuff, right? Because ej times multiplied here gives me h2, and of course this part gives me this thing. And what is on the right hand side? Well, look, h1 has an a embedded in it, so it's an a to the product of all EIs except j's, to alpha minus alpha j. So if this is, if, call it z, if GCG of EJ z is 1, then I get EJ's root of a, right, using Chamir's trick, right? Because I get a root, EJ's root of a to some power z, right? So it's a Chamir's trick again. As long as that power is GCG 1 with EJ, I can now convert it to the EJ's root of a itself. So EJ is a prime chosen during the reduction, by the reduction. It's definitely co-prime with all of these, right? Because these are just other primes. So the only question is, can it be, must it be co-prime with this? And the answer is yes, simply because these are short numbers. This is non-zero and smaller than 2 to the lambda, while EJ is larger than 2 to the lambda. and prime. So nothing like this can be can be not co-prime with EJ. So it's, we win. Yeah. Shall I repeat why this is co-prime?
No, that's fine.
No. Yes. So you can reconstruct how the reduction works, but also why the construction is of this form, right? That it the construction really starts from a simpler one, namely this one, right? Or even simpler would be, let's just compute each root of some fixed value to the hash. Okay, we clearly the reduction can make h to be the challenge exponentiated with a bunch of primes, and therefore it can find these prime roots of the value. But how do you okay, and if the attacker is of first type, then we can do this conversion, except at this point you will have a problem here, okay, because you will just need h of m to be co-prime with EJ. So that's indeed one of the first schemes. So when I listed like a bunch of results, one of the first was like this. It was just h to hash of m for some public parameter h with parts of the public key. But that requires in the verification to check that E is prime, and that's very long verification. The trick to split like this allows just the verification to only check that E is odd, and then the result, even if hash of m is, even if E is smooth, the probability that hash of m is a product of these smooth numbers is not negligible. But when there is this overhang that is information theoretic hidden, that allows this argument to go through. So that's first trick. And a second is, okay, but first of all, how do you deal with an attacker that does reuse, one of the primes? And that is by this split. Okay. Which came down to here. And I guess the upper level, intuition is that, when we look back to the first slides I had, right, which is okay. Now I'm really lost in these notes. But the reduction has to embed some trapdoors in the public key, but generates it with trapdoors. And if adversary asks for signatures, it uses some trapdoors to answer. And when there is a forgery, it uses other trapdoors to extract. And whereas in the random oracle case, we had probabilistic argument for online choice of different trapdoor, here by carefully customizing, we go through and splitting the attack cases. We customize disruptor generation to survive for a given attack case. Okay, and so you have that. Basically, you can see how you can emulate a similar power without the random oracle trickery. At least you have one example for how that could work.
So in this case, in the beginning, we just guess which attack will happen and go from there, right?
Yes. Yes.
No,
so you basically show, okay, let's say that you have 3 types of attackers, right? So you have 2 types of attackers. You have 2 different reductions. One that succeeds with non-negligible probability if the attacker is of the first type. The other that succeeds with non-negligible probability if the attacker is of the second type. Because, so therefore, no matter what attacker you have, there exists a reduction that breaks Strong RSA given that attacker. It's either the first reduction or the second reduction, but that doesn't matter. The reduction exists, okay? And yeah, if you are, you can think of it this way. If you do want a single reduction, then yes, you can guess which of the attackers it has, and it will succeed with probably 1/2 times, the attack probabilities of these 2 reductions given the attacker is of that type. Yes. It sort of doesn't matter how either of these views is good.
Yeah, what I was thinking more of the attacker also being a single one, and he just choosing one of the strategies at random to some distribution, but won't matter. It's still be non-negligible, the reduction.
Yes, because the only thing you care about is that yes. So of course, attacker is randomized, and if we simply say, okay, he's randomized, but let's freeze his coin, because if he exists and is randomized, then let's think of a deterministic one that simply is the randomized one, but he has optimal randomization. He also exists, right? He just picks the best randomness there is. But that is not good, because attacker might choose which way he goes in response to all the stuff. So even if he's deterministic, he might follow some complex code which determines which the forgery based on what he sees. Okay, perhaps using some one-way functions so attacker reduction cannot know which way he's going to go. So, so this basically confirms that, but if his total probability of creating a good outcome is epsilon, and epsilon 1 is the good outcome plus, so this is a probability of forgery, and this is forgery type 1, and this is forgery type 2. Then over all randomness, this is some probabilities such that they sum up to epsilon. So either probability of epsilon is at least 1/2 epsilon, or probability of epsilon 2 is at least 1/2 epsilon, or both. Yes, and so therefore this is an insignificant degradation in the security result, right? Because it's no constant. Okay. Do you have some other questions?
No, not really.
Okay. Right. Right. Okay. So I'll see you next time. Thanks.
Yeah. Goodbye.